We like to describe chemical reactions in shorthand notation, chemical equations. We're going to use the chemical formulas for the compounds that are reacting and being produced. And we have a little notation process that we use. We use an arrow to indicate that a reaction is occurring, and we're going to put our reactants on the left side of the arrow and the products on the right side of the arrow. So what we begin with on the left side, what we end up with on the right side. When we have more than one reactant or product, we use a plus sign to separate them. When we need to state the physical states, we show that after the compounds, in parentheses, S for solid, L for liquid, G for gas, and AQ for aqueous, a liquid solution. If we want to show that we're adding heat, we can put a delta above or below the reaction arrow, and we can give other information such as catalyst or temperature above and below the reaction arrow. If we're trying to predict whether a reaction occurs and it does not occur, we can use NR to represent no reaction. So we write out the reaction given what we begin with, the reactants on the left side, what we end up with the products on the right side. Such as when we cook our food with natural gas. Natural gas is methane, CH4. It burns with oxygen in the air, and combustion produces oxides of all the elements present. So it'll produce carbon dioxide and water. But the problem with this reaction as written is that we seem to create some additional oxygen. We have 2 oxygens on the left and 3 oxygens on the right. We also seem to lose some hydrogen. We have 4 hydrogens on the left, 2 hydrogens on the right. So this reaction is not balanced. It seems to create or destroy matter, which we're not allowed to do. So we want to balance our chemical equations. First step is verifying that all the reactants and products are written correctly. We're not going to balance appropriately if we don't have the right reactants or products. Once we are happy with the reactants or products, we're not going to touch the subscripts anymore. We're going to leave them alone and balance the equation by using coefficients in front of the compound, saying we have more than one molecule of that compound present. We're going to balance one element at a time, go through, balance all the elements, and then come back and verify that the equation is balanced. If we use a polyatomic ion and it does not decompose, we can balance that as a whole unit. We want to use whole number coefficients for balancing in front of the compounds, although we can use a fraction temporarily. So let's balance a couple of equations. So this combustion of natural gas, we go through, we have 1 carbon on the left, 1 carbon on the right, so that is balanced. We have 4 hydrogens on the left, 2 hydrogens on the right. So 4 divided by 2 will give us 2, so we can balance this by having 2 water molecules. We have 2 oxygens on the left, 2 plus 2 is 4 oxygens on the right. So if we have 2 times 2, we'll have 2 oxygens on the left. So this balanced equation, we did not unbalance any of the chemicals in the process. We have carbon, carbon, 4 hydrogens, 2 times 2 is 4 hydrogens, 2 times 2 is 4 oxygens, 2 plus 2 is 4 oxygens. And if we needed the physical states show up right after. We have gaseous natural gas, we have gaseous oxygen, we produce gaseous carbon dioxide, and we produce gaseous water. If we burn acetylene with oxygen, we still produce carbon dioxide and water. We have 2 carbon atoms, so we need 2 carbon atoms in the products. We have 2 hydrogen. We have 2 hydrogen. We have 2 oxygen. We need 2 times 2 is 4, plus 1 is 5. So we have a odd number of oxygen in the products and only even oxygen in the reactants. The carbon and hydrogen are balanced, the oxygen is not. So we can do a fraction as a temporary measure here. So we have 5 oxygen divided by 2 gives us 5 halves. 5 halves times 2 is the 5 oxygen we're looking for. But we don't want to keep that fraction. So the equation is balanced as written right now, but we want to get rid of this fraction by multiplying the whole equation by that denominator, that 2. So we multiply 2 here, 5 halves times 2 becomes 5. 2 times 2 is 4, and then 2 times 1 is 2. We check, we got 2 times 2 is 4 carbon, we have 4 carbon. 2 times 2 is 4 hydrogen, we have 2 times 2 is 4 hydrogen. We have 5 times 2 is 10 oxygen, we have 4 times 2 is 8, plus 2 is 10 oxygen. Let's do one more. One way to reduce a metal oxide into the pure metal is using carbon to extract the oxygen. That carbon is in the form of charcoal or coke. So we have 2 aluminum, so we're going to do 2 aluminum over here. We have 3 oxygen. We have 2 oxygen. Well, 3 can't divide into 2, nor 2 into 3. So we do the common factor. We're going to do 6. So we need 3 times 2 will give us 6 oxygen. 2 times 3 is 6 oxygen. Well, I have unbalanced the aluminum here, so I'll go back and readjust that. I need 2 times 2 is 4 aluminum. Now for the carbon we have 3 carbons, so we need 3 carbons.